All right, all right. Thank you so much for joining this session. Today we're going to talk about Cosmos DB, how to design and implement. We're going to present you a live use case and go through all the goodies. It's going to be lots of fun. But first and foremost, let me introduce my sidekick, my co-colleague here, Andreas.
Hi folks, I'm Andreas and I'm part of the Fast Track for Azure program, helping customers like you to onboard safely and with confidence within Azure. And I'm here today with our guru, Cyrille, in Cosmos DB, and we are gonna discuss about the best practices regarding SQL. So Cyrille.
All right, this is going to be fun. Thank you, Andreas. So my name is Cyrille. I'm a fast track engineer, colleague of Andreas. I specialize in open source databases and Cosmos DB. And I will be before going into the session. By the way, let's move to our next slide. And say also hi to our moderator. So for our chat, we have another colleague who is monitoring the chat, and she will be answering all your questions or bring them live in the studio with us so that we can answer your question. So all the content we are going to present today is actually present and freely available on this URL. So you can scan off the QR code. That will automatically bring you to this URL, which basically is a collection. The collection consists of two things, essentially. The first is a learning module. You can go through all the content, self-paced. It provides all the code, and it's a great module if you want to learn a bit more about optimizing performance for Cosmos DB. The second piece of content are two external blog posts which are published on the Cosmos DB developers blog. Those blog posts contain an end-to-end scenario which walks you through all the essential query troubleshooting and performance recommendations we most of the time see.
So basically, most of those content is actually written by our guru, as I mentioned before. And this is actually the content that we're gonna go through today. And today's learning objectives are, we have 3 learning objectives. The first one is to help you understand how Cosmos DB is working so that you can understand what is the best model you can, data model you can put in paper and then in practice, so that you can support a real life application. The second part is we are going to fine tune a couple of queries, hoping to show you the tools that you can use to fine tune your own queries. And the last piece is going to be about monitoring the live system and potentially figuring out various bottlenecks or things that you can improve your performance or your cost. So with that, Cyrille, would you like to take us down whiteboard so that we can understand a little bit better how Cosmos DB is structured and what is Cosmos DB?
Yes, very good point, Andreas. Let's do that. So let's stop with the slide sharing. Let's minimize this guy a bit and let's switch to the whiteboard. So in order to do some good data modeling for Cosmos DB, it's quite obvious, I would almost say, that you should know a bit how Cosmos DB is actually structured and how it's built up. So let's just pick this whiteboard and start drawing out. So when you create something like Cosmos DB, the first thing you create is an account, right? And on the account, there are a couple of settings which are literally written in stone. And these are important settings. There are also a ton of settings you can change at any point in time, but I highlight the ones which are basically set in stone. And the first one is the API. So I'll excuse my P here. This is an horrible P. So the first one is the API. Cosmos actually has a couple of APIs, 5 in total: SQL, Mongo, Cassandra, Gremlin, and Table. Today we'll be focusing on our SQL API. Once chosen, you cannot change to a different API. It would require spinning up a new account.
And isn't SQL API the most favorable of all? I mean, the one that has the latest and greatest features?
That's indeed true. And there is actually a good reason for it, because it's the one and only API where the client SDK is also developed by us, which means this client SDK actually knows it's talking to Cosmos. For the other APIs, that's not the case. So if you pick, for example, Mongo, the client is just a MongoDB driver. It thinks it's talking to Mongo, and it talks to Mongo, but essentially it's still Cosmos DB. And for that reason, the SQL API is actually labeled the core API. And that's because we have a couple of features which are Cosmos specific in this SDK, which of course are not available in the other APIs. Thank you for highlighting that, Andreas. So the second thing, which is, which you have to set on account creation, is zone support. So when you deploy Cosmos DB, you can say, you know what, I want to deploy the various nodes across multiple zones or not. In terms of resiliency, if you do that, you have to do that on account level. There is a workaround to make existing accounts zone aware. But hey, it's a workaround. So let's do it right up front. And the third one, well, if you don't trust Microsoft Managed Keys and you want to bring your own key because you have stricter security requirements, for example, you can set your own customer managed key to encrypt the data in Cosmos DB. This is something you can only set up on account creation. There is no way to change it later on, for obvious reasons, of course, because we have to recrypt, and at scale where Cosmos is built for, this would be a too long running operation.
Of course, set on stone. This sounds a little bit scary, and this is why we have automations like ARM, Bicep, or even Terraform that you can use in order to, if you got it wrong, you can automate the whole process and provision a new account. Of course, there is a migration if you already have data inside that account, but still, all those ARM, all those infrastructure as code techniques are in play here to help you automate the provision of those accounts.
Yeah, exactly. Good point, Andreas. So let's dive a bit deeper. Once we have created an account, the next thing we typically create, it doesn't make a beautiful box. Let's give it a retry. I like beautiful boxes. Once we have created an account, I should not give it a retry. There we go. Of course it doesn't work. Anyways, once we have created an account, we create a database, and we can have one-to-many databases, basically. On a database, we can provision RU. This, however, is something you preferably should not do. When you provision RUs on database level, it's going to change. It's going to change the partitioning. That's one, and it's going to make it less predictable what's going to happen. Yes, Andreas, you were.
Let me
say something.
Let me try to explain this a little bit better. So imagine that RU is the horsepower, and basically the database is a warehouse where you have a lot of cars in there. Basically, what you are telling is that you can provision a horsepower number on the level of a warehouse, and basically all your cars will be sharing this horsepower. But this basically means that each car, the performance of each car is going to be totally unpredictable, and it will be very hard to troubleshoot why is that car doesn't perform that well, because RUs, the horsepower is provisioned in all of those, in all of this fleet, and basically you have to you can't control the performance then on a sub level that we are going to see right now.
That's a very nice analogy indeed. So if there is one takeaway, please try to avoid this. There is a reason when you should do this, and that's, for example, when you want to create many containers and the majority of those containers are going to be idle for the majority of the time. Then this actually makes sense as a cost saving measure in any other sounds a bit, but in the majority of situations, you do not want to do this. It makes it just less predictable. All right, let's dive a bit deeper. So underneath a database, we have something like containers, and it makes a beautiful box. And this is called differently per API, but for SQL it's called containers. On a container, you have something which you have to be very mindful about, because once created, you cannot change it anymore, and that's the partition key. So when you create a container, you are required to also set the partition key. Once set, you can't change it anymore. Right? Other things which are here is RU provisioning. This is where you should do it because it's the most predictable way of provisioning your RUs within Cosmos. Things like index policies and other options like TTL, encryption policy later on, and so forth. These can all be changed. Yes, Andreas, please.
So this is the container is the place where you start putting the documents, your information, the thing that you're going to be storing. And TTL is time to live. It's one of those features that Cosmos DB provides. But Cyrille, why is it that important, the partition key that you have there? I mean, why can't I change that?
Okay. Let's dive a bit deeper into this guy. So what does this actually mean? Well, imagine we are going to model something with the family, right? And we choose as a partition key last name. Imagine that. That actually means that all documents with last name Visser will end up here. Or are logically grouped. And we call that a logical partition. All documents with last name Botsikas are basically grouped up here. So in another logical partition, and so forth. So this guy here, this logical partition, actually has a hard limit. And that hard limit is 20 gigabytes, which means that, well, you cannot outgrow these 20 gigabytes. No more 20 gigabytes of documents for Botsikas.
That's bad because my family actually spans across the world. We have Botsikas in Americas, we have Botsikas in Germany, we have Botsikas here in Greece. Does this mean that I'm doomed? If we reach the 20 gigabytes, no more Botsikas are allowed?
Yeah, well, if you want to grow your family and you don't want to be restricted by Cosmos DB, you have to really ask yourself the question, is the Botsikas family going to supersede this 20 gigabytes? If the answer is yes, well, then you need something else. Maybe you need something like last name plus country, for example, as the partition key value. And this makes it already a lot more granular because then you get a logical partition for Botsikas Greece and for Botsikas Germany and so forth.
Perfect. So this means that of course, perhaps the country is too small because otherwise, you may get so many logical partitions. Does this affect somehow the speed, the performance of the database? Should I potentially choose a region like EMEA Botsikas and Americas Botsikas in Asia?
Yeah, that's a good point again, Andreas. So in order to answer that question, we have to dive a bit deeper. So again, this is actually unlimited. So you already see a bit how Cosmos scales, right? It's horizontal. While vertically, I immediately hit a hard limit here, which is 20 gigs. Horizontally, well, I can have many logical partitions. There is actually no real limit for it. Well, at some point, the limit of the data center, and we come to that now. So underneath a logical partition, we have our final layer, which contains compute and storage, and we call that the physical partition. So this is actually where all these documents come up. This guy, let me do it like this. Yes, here we go. This guy here has limits as well. And let's also pick red. I love red when it comes to limits. So it's 50 gigs and it's 10K, 10,000 RU. So this means if I'm going to store more than 50 gigs of data, I'm automatically, without me noticing it, get another physical partition. And Cosmos is going to do the mapping. So for example, like this. And this is our Cosmos skills. And again, this one doesn't have any limits. It can be as many as you like. The scale out here literally happens on, well, if you store more than 50 gigs and or whether you need more than 10K RU. If one or both of these are true, you automatically get a new partition, and that's with every interval.
Perfect. So this means that basically, while the logical partitions grow, then at some point of time, if you get 3 logical partitions that are really close to 20 gigabytes, they will actually be split among 2 physical partitions, so that they can honor this 50 gigabyte limit that you placed there. And then I see the 10K RU, the 10,000 RU units. Can you help me understand a little bit what 1 RU is? What is the operation that costs 1 RU?
Yes. So let's talk a bit about that. So first and foremost, RU request unit is the Cosmos way of abstracting computer storage. So let's see what 1 RU is. If we think about a 1 RU operation, so everything in Cosmos costs RU, every operations. But if we think about a 1 RU operation, the most efficient one is that first and foremost, I have the partition key. So this means I know exactly where a document is stored, because it's stored on a physical partition, and a partition key value like Botsikas can only end up at one physical partition. So I'll immediately know to which server I have to go to, basically. By using something like the ID, which uniquely identifies the document, I immediately know that on that physical partition, I need to look up only that document. I don't need to scan, I don't need to seek, I just need to look up that one doc. And that's what I then essentially return. This is what is called in Cosmos DB a 1 RU operation, and there is actually a lovely name for it. It's called a point read. Nice. So a lookup of a single document by using the partition key and the ID, right?
Oh, perfect. So this means if I know exactly where I'm going, I can have, this is the minimum cost I have to pay. And now it makes sense back in the previous diagram, where if I split out my family per country, this means that probably they will end up in different partitions. So when I will be asking, hey, bring me all Botsikas, I will probably have to go through all physical partitions to figure out if there is a Botsikas in that region. So this now makes sense. Okay, perfect.
Yes, and that's what you call a cross-partition query, if you want to do that. And yeah, sometimes people think that's a problem. Well, like almost with everything, it depends.
What I see there is that what happens, I see that red down below the 10K RU. So what happens if I reach that? I mean, if I have some hot logical partitions all together in one physical partition, and I reach those 10K, what will happen then? How Cosmos DB?
Yeah, so if you reach that 10K, well, first and foremost, it depends a bit on, of course, what you have provisioned here. So let's say I have provisioned here 10K as well, right? To make it very easy. When I am using 10,000 RUs for any given second, because RUs operate on a second basis. So when I use those 10,000 RUs and there is one additional operation coming in, forcing a bit more RUs, then by default Cosmos will say, no, client, just back off. I'm too busy, go do something else. And then the client says, oh, okay, sure, I'll back off. And it will basically queue up his request and retry it a bit later. And that retry interval and the amount of retry times is something you can configure in the client itself. By default, it's up to 9 times 30 seconds per time.
So this is the default 4 to 9 throttled message that the client is getting, and then our clients, the ones that we have created, have some retry policies baked in there you can select from. Awesome.
Exactly, exactly. You do not get that with the other APIs. It works slightly different per API. With the SQL API, however, this logic is built in the client, and it makes it very straightforward to queue up and retry later.
Thank you so much, Cyrille. Actually, if the audience has any questions, you can type it in the chat window, and we will be able to address those questions. But for now, what I would suggest is that we go and see, now that we understand a little bit better how Cosmos DB is structured, let's deep dive into one scenario, like the marathon scenario that you have prepared for us.
Yes. So let me. Bloody. This always goes wrong. Sorry about that. I'm not so good in slides. Anyways, here we are again. This is the one of the final slide, because the rest is just Portal and a bit of Visual Studio. But to give you a bit of context, this is our use case we are going to address today. So we have been given the task to create a leaderboard for sports events. And those sports events can be any type of event, right? Which also means it can be, well, not any type, but the data can be quite different. For example, for a marathon, you would only have one score, while if you have a triathlon, you're going to have multiple scores, like for the swimming, for the running, and so forth, and cycling, of course. So your schemas are going to be different. For that reason, it already starts to make sense to look more at the schema-less approach, which Cosmos DB is. It's a NoSQL database. Also, the ingestion of these files are going to be completely JSON-based. That's another thing which drives us towards a Cosmos DB implementation. And finally, the solution needs to be very scalable. Sorry about that. It needs to just be scalable. So it's hard to predict how much data we will store. Expectation is it will be way more than 50. But yeah, if we decide to keep our data, this is going to grow exponentially. So it needs to be scalable.
So basically, this is why we are going to be using a single collection, and we're going to putting in all those documents. And as we can see, for example, the top document has a score, while the other one has a total score property, and we will have them all together there, and we'll try to see some queries that are going to be asking for this data.
Yeah, exactly. And when we see a JSON like this, and now that we know that partitioning and Cosmos DB is so tremendously important if you want to scale, and yeah, we need a scalable solution here. Let's just start with the choosing the partition key. And when you choose the partition key, the thing you actually don't do is think about Cosmos or think about your data even. You're going to think about, what is my application doing? And let me bring up the whiteboard again. Yeah. So we are going to think about, what is my application going to do? What are my most dominant queries? So what queries I'm going to run all the time, right? And this is quite important. So we have to identify our top queries. If our application loads, it shows a leaderboard, maybe the home page. The queries which are going to be executed almost all the time, that's what we're interested in. And we should have top 5, top 10, pick your number, but at least a top amount of those queries. And of course, we did a bit of homework. So let's bring this one up. We've come with 4 queries. I mean, 4 was sufficient. Why pick 5 if 4 is sufficient? But these are our top 4 guys and girls. So the first query, which is going to run all the time, is well, show a leaderboard of any given sports event, and it will be looking something like this. And our second query here will show all the events for a particular year where a particular person has participated in. Okay. And then we have our third query. It wants to show additional information, maybe a bio, some top scores, history, you name it. It at least wants to show information around participants for a given event. And once we have seen all these participants for a particular event, well, we want to dive into depth and pull up information regarding a particular person, right? So those are the 4 queries which are expected to run all the time. And this is what we have pulled from the application design. Now back to Cosmos. Now that we know which queries are dominant, let's examine those queries. And when we examine those queries, it's very important to see where they're filtering on. You're always filtering, basically. So we are going to look in SQL case at this where clause. And here we see that event name, event date is present, event date again, and participant ID. Okay, cool. Event name again, participant ID, and event date. So
if I bring in my SQL design, we're trying to figure out which are going to be my primary keys or something like that, or the way how I'm going to be clustering those records so that I can optimize the engine to respond to my queries.
Exactly. And we see here that the majority of the queries actually has event name. Right. And this makes sense, because if we would pick event name, then we know that all of these queries are going to hit just one physical partition, which is good. So that makes that event name is actually a good partition key. However, there is one more question we should answer, and that's the storage. Does a particular event generate more than 20 gigabytes of storage? If the answer is no, we're good. If the answer is yes, event name is not the right partition key.
But I feel that even for the Greek marathon, which is more than 400 years old, it's I don't think we are gonna reach the limit of the 20 gigabytes, because the documents are so small, right? And the only thing that counts is how big is the document, and basically this is the 20 gigabytes that hard limit that we have, right?
Yeah, exactly. That's a good point. So even if you pick the oldest the sports event to date, that's not going to generate more than 20 gigs of data. So from that perspective, if we choose event name, that's check in the box. If we take a look at the queries, all these queries filter on event name, almost all of them, that's also check in the box. And which makes event name actually a very good partition key. And this is the bit of reasoning you should do when you're trying to identify the right partition key for your scenario. You just think about your application. You think about the most dominant queries. It doesn't have to be all, but you're looking for those queries which you find thousands and thousands at time, every single minute, for example. And then once you have found your ideal property, you just ask yourself, for this property, do I really expect that it's going to be 20 or near 20? And if the answer is yes, well, we have to keep searching. Maybe we do a combination, event name, event date, for example. That would be a good combination in this case. Or if the answer is no, well, we have found a partition.
Perfect.
All right. So a bit about cross partitioning, because we see here, if we choose event name, this guy here is actually not really down drilling on event name, right? You see that? It's just event date.
So this means that I will have to look for all our partitions.
Exactly.
Find that.
Exactly. So let's examine now if that's a problem, and in order to understand. Well, in order to understand whether that's a problem, we go in a bit of theory, and the theory is like this. So if we have a query, for example, and that query uses, let's say, 10RU. So I have a query, I execute that query, the query executes 10RU. When a client sends this query, then essentially Cosmos DB will, if it's filtering on the partition key, so event name in our case, right? if it's filtering on event name, then Cosmos DB will exactly know where it is. So we are going to hit directly the physical partition, and then return and return. And this is beautiful. 10RU, we know exactly where it is. But what if we are not filtering on event name? What if you are filtering on, for example, event date, right? Well, whether this is a problem or no is really, it depends. And it depends is this. So if I just have one physical partition because I only store 50 gigs, and I'm not using more than 10 KRU.
So basically, all your logical partitions are not more than 50 gigabytes. This is actually what drives this limit. Okay.
Exactly. So once I don't have anything more than 50 gigs combined, I will only have one physical partition, right? And then even if this is a cross partition query, well, yeah, there is just one partition, so it's going to cost 10 RU. But what if I at some point then have two? Well, what's then going to happen is that my query is actually duplicated. So you will see that Cosmos says, oh, wait, event date, I don't know where it is. So let me just ask both physical partitions to return documents where event date is blah. And it will execute twice, which means I'm already consuming 10 plus 10 is 20 RU. So this one is now not a 10 RU query, but a 20, and actually slightly more because we have to do a bit of aggregation here. So it's going to be slightly more than 20.
Right. So this means that if I go into my database and I provision something like 20,000 RUs, this will force Cosmos DB to span out. And although I think that that would be a good idea, actually I will start paying double the cost for some queries, especially if I don't specify exactly the logical partition, which then translates to a physical partition, to specific physical partition. Thanks.
Exactly. So, and what if we grow even more? So what if we, for example, have up to 20 of these boxes? So we store 1 terabyte of data in Cosmos DB. So what's going to happen in that case is that, oh, my query is replicated 20 times, right? So you get this ID, and every time it's 10 RUs, which means it's becoming now 200 RUs already. And this is an optimized query. We cannot optimize it any further. And when I have a query which always consumes 200 RUs and it's a dominant query, it's executed all the time, yeah, well, then it's going to be expensive, because this means if I have this one query and I expect that I have, for example, always 10 concurrent or even 100 concurrent users, that's what I expect, 100 concurrent users. That means that I need 200 times 100 is 20K RU already just for this query. And that's what I need to set on my collection. And this is where cross-partition queries start to hurt. So if you have a scenario where you have a continuous growth in terms of data or in terms of concurrent users, for example, and because of that scenario, you will get more physical partitions, and more is like way more, because with 2 or 3, we're still fine. It's going to be a bit more expensive, but not that much. But with 20, you will see that it's already quite an impact, right? That 10 RU became 200 RU. And that's just a single query. And what if it was not optimized? It would even be more.
Right.
So yeah, so this is, yes, Andreas. Sorry.
So this is why it's so important to pick the right partition key based on the actual usage that you're going to have. So this is why we have to keep the web application that's going to be consuming this Cosmos DB on mind, and design then the data model based on that, based on the queries that the app is going to be doing. Perfect. And how can we figure out how much is the actual cost? This 10K, this 10 RUs that you mentioned, is there some way I can see, for this query, I'm paying that much, I'm paying that much?
Yeah, that's a good point. We can see that. So let's now dive into the first cycle of our development. We know our application designers and developers are busy creating that application. From a Cosmos DB perspective, we are going to create queries, and we're going to tune them. And when we first start, actually the portal, well, it depends a bit on what you like, but the portal is quite good as a quick reference whether your query should be optimized a bit or not. So let's examine that. Let's go through the portal. Yeah, here it is. And I'm in the portal now, my Cosmos DB instance, as you can see. I got this guy. Let me close this database to give me a bit more real estate. Already created a database here called sports. We got one container. It's always good to start out with one. There is no, well, it's always good to start out with one. On that container level, we can go to skill and settings, and what we then actually see is that we have provisioned our use here, so manually 4,000. We exactly see the billing here. Cosmos RU billing is per hour, as you can see. And if I would be using 4,000 manual, that means that every hour I'm using these 4,000, and this is going to be my bill. There are a couple more things, settings. You can see here that the partition key is grayed out. Like I said, once created, well, it's created, dot. There's no way to change except doing a migration to a different container. And finally, the index policy. This is already a tuned index. By the way, if you would create a standard container, you will see that Cosmos DB will index all properties. And this is actually fine when you start with development, but be very mindful. This is something you don't want to do in production, because especially with JSONs which are bigger, every time all these properties will be indexed, and that basically makes the index also grow besides your document storage.
So this is the typical dilemma we have in any database design, that if you put too many indexes, you're optimizing your search and queries, but on the other side, you have this penalty on the insertion side, insertion time. So you have to find the sweet balance between over indexing and under indexing. And the cost, the index size doesn't count in the 20 gigabytes limit that we had. Perfect. So it's still just the data that we are putting in that container. Perfect.
Exactly. So think about it like this. When I write a document, I have to do two things. First, I have to write the document to disk. And secondly, I have to update the index because I have a new document. And the bigger the index, well, the more time it takes. And the more time means the more RUs also. So in order to optimize latency and optimize RU consumption, it's always good to only index the parts you really need in your queries. When you start out, please go with the default because it makes it easy, but just don't forget to tune it. And tuning is actually quite easy. You start with excluding everything, and then you just include the parts on where you filter them.
Perfect.
All right. So let's now dive into our queries. How can we see that our queries are actually behaving as they should behave, right? So let's pick our first query. And the first query is that we actually want to show a leaderboard. So give me the top scores for a particular sports event on a particular date. Right. So
we already see here that you're in the query, you have the event name. So we're hitting a specific partition. And you are also querying about event date, which is in the index, if I remember correctly. So
yeah,
awesome.
That's correct. That's correct. I'm not sure why. Oh, here it is. Probably. Yeah, there we go.
Perfect. So you just select star, bring me everything from that container where the event name is this one and the specific year. So for one event, specific year, and perfect.
Yeah, exactly. And what we see then is the portal returns a bunch of information. This is something we can actually limit. I've put it now to 30,000 to give you a very good understanding. The default here is 5,000. But when you put it a bit to a higher number, like I've did here, it's easier to fetch queries like this one, which returns 30,000 documents. As you can see, the documents themselves are very small. They are nicely ordered. Everything is what we expect. So let's take a look now at the query stats. So we can see that pulling those documents here, as you can see, costs around 1120 RU. We call this an expensive query. Yeah? So imagine I'm going to run this 10 times every second. Oh my God. I would, for this query, would already need 12K RU. That's not fun.
Right.
That's not fun. And why is that then? Well, in order to understand that, we have to examine the stats a bit more. So it's going to retrieve 30K of documents, and retrieving 30K of documents. Well, Andreas, you can do the math here.
That's
How much would this be, huh?
Oh, that's almost 13 megabytes, right? If I see correctly.
Yeah. So it's going to retrieve 30 megabytes of document, and look what it sends back to the client.
So basically, what you're telling me is that I on my web page, if I stream the response back to a web app that is going to try to deserialize 15 megabytes of JSON, I think this is enough for any modern browser to crash, right? It's
yeah, and especially if you would do that multi-threaded, huh? So multiple of these guys hitting the same instance. That's just not going to be fun. And we do see we're using the index. That's cool. And we also see that the index lookup time is quite well. 2.25 milliseconds. Of course, we can optimize that a bit. But even if we would like have a 100% optimization here, going to 1 millisecond is not going to fix our problem. And that's because the majority of RU consumption is caused by this guy. So whenever you see high RUs, this most likely, this one is going to be the one where you'll be looking at. So we see that we spent 228 milliseconds here on loading the documents, which makes sense. We have to search 30,000 documents, load 30,000 documents, return 30,000 documents. That takes time, right? So we also see that the query engine also spends a bit of time.
Right. So basically, the cost of a query is twofold. The first part is searching through those logical partitions and finding the information, and then actually retrieving that information and loading that information.
Exactly. So back to our use case, because we clearly need to optimize this. This is like almost silly. There's no way we should return 30,000 documents. So our use case says, I want to have a top score. Well, I'm not sure about you guys. Yeah, on a leaderboard, right? Yeah, I want to have a leaderboard with 30,000 items. So I'm not sure about you guys, but after reading through the first 100 at most, I get very tired and probably would close the leaderboard. I'm just not interested. And if I'm interested, because like my brother or myself is participating in, and well, it wasn't too fast. Well, then I would look up myself, right? Which is going to be a different query anyways. So in order to optimize this guy, there is actually one thing which is really nice. So let's say I want something like top 100. Give me the top 100. And in Cosmos, if I use a top with an order by, what is going to happen is that Cosmos will fetch the 100 first ordered documents. So it will be automatically already ordered by total score, and it will fetch the first 100. And after that, it won't bother looking at other documents at all. So let's put this into action, and let's see what is going to be of a difference. And be very mindful. We were at 1121, so let's see if we can bring this a bit down. So we're going now to 100 documents. Let's examine the query stats. We're down from 1120 to 6.7. Which is awesome. And that's indeed because we only need to retrieve 100 documents.
So basically, in the previous scenario, you could only have 3 concurrent users doing this query, because then you would reach the 4K limit that you provisioned for our use. And now you literally nailed it. I mean, perfect. Okay, so basically, what you just did is read only the data that you care about, right? Okay. So this do in the other times, on the times that we were seeing before?
Okay, cool. So we see that, well, it returns, what is it, 4 kilobytes? Not even. How to do math on the fly. Anyways, there is the response object being sent is a bit bigger. Okay, we might be able to tune that, but 6.69 is already quite good. We can see, because it's just 100 documents, the index lookup time is also quite faster. And the real difference here is this guy. See that? So we're down from 220-ish to 2-ish. Love that.
Right. That's
So,
awesome. But can I see back the results?
Yeah, sure.
So do I really need those underscore RIDs, attachments?
That's a good point as well. So the select star is, well, in a relational database world, is something you really should not do, because often it pushes the engine to not use the index at all. In Cosmos DB, you can do it. However, the big penalty you're going to pay is the serialization of the response object. So you see here, I'm going to output 100 documents, and this is my document size. And creating a response object with this size, of course, also costs RU. Right? It is a bit of compute which is necessary. So let's examine what's going to happen and look at that 6.69 if I just return a single column. Why not? So single column returned, as you can see. And we're dropping here a bit. That's expected. I have a small JSON, a very small JSON, but we're dropping a bit. And that's because, look at that, the output, so the response object, which is sent back to the client, it's just way quicker to serialize. So we can also tune that, and this is especially very useful. Well, it's actually always useful, but especially with large documents. So if you guys and girls are looking into the multi-kilobyte JSONs, a select star, well, that's something you really can improve, because it's going to use much less RUs.
Nice.
Right. So let's go to query 2. So query 2 was our is a query where we don't use the partition key at all. We basically filter on an event for a year and a particular guy, and that's what we, or girl, and that's what we group up. So let's execute this guy or girl. So here we go. Only 3 results. So apparently this year there were only 3 sports events. Okay. The year is not finished yet, so that kind of makes sense. And we see that this query here consumes a bit less than 6 IUs. A bunch of zeros and a 1, but well, it's a bit less than 6 IUs, right? We don't care about all these zeros. And well, a response object is also quite good. Index, again, an index lookup, we love that. 0 to 27 milliseconds, just not optimize that. It's not going to be much of a thing. So we spent just 1.5 millisecond on document load. Query engine was also done in a breeze, or in some almost unmeasurable time. So this is all good. Now the question we ask ourselves is, okay, this is cross-partition query. It runs super efficient. But yeah, I only have, how many documents do I have? Let's quickly see, right? So if you want to see how many documents, you can do something like this. So we only have 100,000 documents, right? Only, yeah. It's well, what if we have like 100 million? So what if we have a lot of data and many physical partitions? So not 1 or 2, but more than 10. Yeah, well, if we have more than 10, this 5.58 becomes more than 58. At that point in time, it might be interesting to start optimizing it. Maybe not even with 10. With 20, however, 116, well, if you only use 4,000 RUs, if this query is executed so many times every second, that 4,000 RUs is going to be reached quite quickly. So in those cases, you want to optimize. If you think you only will store like 50 or 100 gigs of data, yeah, 5 versus 12 for you, it's quite optimal. We can leave it like that, right? So that's a bit the reasoning what you have to do with cross-partition queries. They're not always hurtful. It really depends on how much data you store. All right, let's go to query 3 here. Query 3 is a different query. We basically want to see, well, participant information for a particular event.
So basically, for
done. For some reason, the browser likes to do this, teasing me. So yeah, for a particular event, and we can see we're going to return 30,000 documents again.
Right.
So let's examine the query stats. Look at this guy, 938.
Again, so only 4 concurrent queries we will be able to make.
Yeah, after 4 concurrent, we are done. Or we have to say, you know what? I'm going to add more than 4,000, but adding more than 4,000 means also that the pricing is going to be different, because with Cosmos, for the provisioned one, you do not pay for query, you pay for whatever you provision on the container or database level. So if you provision that 10,000 RU as part of a container, that's what your monthly bill is. And for that 10,000 RU, depending on how efficient your queries are, you can run that many queries concurrently, right?
Right.
So in order to bring that down, well, if we optimize our queries, we can do more for the 4,000 RU, or we can say, you know what, I'm going to pay less. I'm going to make it 2,000 RU. Hence the query optimization. So back to this guy, request charge. Okay, that's too high, and we again see this figure. What is this? 3.6. This is something like 2.5 megabytes.
Yep.
Yeah. Not fun. Or more even. I don't know.
Good document. Wow.
Yeah. We see that the index is blazingly fast. So let's just not spend time on the index here.
You are basically hitting exactly the event name, which is the partition key. So it's directly.
Yeah, which was also indexed. Yeah, one partition. We erase across the index. We get our documents, and that's it. From the seeking point of view. But then we have to load all these documents, and you see this number again, because we have to wrap them in a response object and send them back, right? And that costs time. And time is definitely not fun here.
So we have to think of a way to reduce the amount of data that we're reading, right? So
yeah,
we cannot reduce the columns. I mean, we only are selecting 3 columns, right? So what is this for? Why are we using, why do I want to list for an event the whole people? And I mean, if I design a web application and I get 30,000 records, am I gonna show them in one go, or?
Yeah, typically not that. Typically you would do something like pagination, like a next button, or when you scroll down, that the next set of results are loaded.
Where you're scrolling and you're progressively loading the information. Awesome. So can we do this with Cosmos DB?
Yeah, there is actually a way of doing this. But before doing that, let's examine. So what would happen if we would add our top here? Well, we could do that. The only problem is we don't have an order. So we are just going to randomly, between quotes, return 100 participants. But we don't know what that user in the application is looking for. So maybe it's just browsing through a list, right? So we need to have, indeed, pagination. Otherwise, it will be hard to fix. And we can't do this on a query level. Fortunately, Cosmos has a built-in pagination feature, so to say. And in order to understand that, let's spin up the whiteboard again. And then we talk about it conceptually, and I show you what you have to do in the SDK. So in code, because we can't do this on the query level. So think about it like this. I have a client. And my client is going to execute this query, right? Our query here, which was query 3. Yeah, there we go, query 3. And by default, if we don't do anything, it's just going to return that much of data. So we have to do a couple of things. So the first thing, what we are going to do on this client is we're going to set a max. It's called max, and I'm going to write it out once, item count. And we can set that to, for example, I only want to see 25. I only want 25 results, for example.
So this is something that I do not specify within my query, but on some additional options that I will be sending through the client. Awesome.
Exactly. That's what we set here. So then this query is sent to Cosmos, and we add this option of, just return 25. Well, Cosmos in our case is going to look up that query. So let's assume we have here a big index with all kinds of documents, and it's going to look up that query, and it will start at the beginning. And here it's going to return those 25 documents, and those are being returned to the client. What it also does, and let me put the 25 here to give myself a bit more real estate. What it also does, it also sends back a token. So it actually sends back a token which says, you know what, I have stopped here. So I've read the first 25, I stopped here. A token is generated under the and a token is actually sent back as part of the response object to the client. So the client will get its 25 documents, so the result of the query, and a bunch of properties. And one of them is the token.
Right. So like a bookmark, here is where I stopped. This is the page where I stopped.
Exactly. So this is what's sent back. Now, for a subsequent call, so the client should cache that token, and when a user clicks the next button or starts scrolling down, a new query is executed. And we're going to do the exact same thing. So we are going to execute that query again. We're going to say, I only want 25 items.
Mm-hmm.
However, I'm also going to send the token to Cosmos. And what Cosmos is then going to do when it executes this query, it's not going to start here. It's going to start here. It will read the next 25 documents, send it back along with a new token, and so forth. So this is how pagination works. At the client, you set the max item, you execute your query, you return your 25, you capture the token, you store it, and the next time a user hits the next button, you execute that query again, but this time you add the token, telling Cosmos, no, do not start at the beginning, start at where you stopped.
Perfect.
Right?
Perfect. And so, how does this look like on the code side? I mean, where do I pass this max item count?
Exactly. Let's take a look at that. So let's open up Visual Studio here. And let's go to a bit of code. Let's go to my new query. Yes, here it is. So I hope it's good readable.
Yep.
All right, perfect. So what we see here is our query. You see that? This is exactly the same query.
Whoa.
We do a parameter.
Parameters, no more SQL injection.
No. Yeah. You can actually send a clear text query. Please do not do that. Cosmos also knows something called SQL injection. So it's easy to say, you know what, give me, add a clause like or 1 is 1, which is going to return all the documents, also the documents you should not see. So yeah, always use parameters to prevent any form of SQL injection, right? What we also see here is that we're going to use the continuation token, so declaring a variable, set it to empty first time. And what we then do here is we basically execute the query. And when execute a query, we submit the query, which is here, this line. We start from scratch first time. So no continuation token, we just start from scratch. And we tell Cosmos, you know what, I only want 25 items.
Perfect. So when you don't have a continuation token, you just pass null to that.
Exactly. Then you tell Cosmos, you know what, I don't care, just start from scratch. No.
And you specify the max item counts in query request options. Nice. Okay.
Exactly. And then we capture the response. That's what we do here. We do something useful with the response. I don't know. This is the application designer. But the real thing, what we are going to do, we are also going to grab the continuation token from the response object. And we are going to cache it. So you would cache this somewhere. So that the next time the user presses, for example, the next button, or scrolls down, however you want to implement it, we are going to do exactly the same thing, but we execute our query, and this time we do set the continuation token value. And we again say 25 items. So this tells Cosmos, don't start at the beginning, start at where you left, and give me just the next 25. Yeah.
So basically, you're giving back the bookmark. And how do you know when it stops? It just stops bringing results, right?
Yeah, exactly. At some point, there are no results anymore. That's what this guy actually is. And when there are no results anymore, we're done.
Perfect.
So let's see this in action. Let's quickly run it. Yeah, this is readable. I hope it's readable.
So this is the source code that you will find on the GitHub page, and the link to the GitHub page is within the learning module on the blog posts on the bottom with the resources. Yeah. And what we're seeing here are the queries, and we're going to be running query 3 and 4, the next one we're going to discuss. And first we run the query as is. So we see that the 900, is it 500? 938 RUs that are being consumed. And now we're going to run the optimized one, where basically we're going to do the pagination trick that Cyrille just showed us.
Exactly. There is also a bit of end-to-end latency. You can see this is quite high. This is due to two factors. First and foremost, it's the first time I execute a query. Whenever you do something the first time with the Cosmos Client SDK, it's going to do a ton of connection pooling, caching, and so forth. So the first call is always expensive. Secondly, I'm not in Azure with my client, so there is also a bit of remote latency here. But you see 938, not so fun. Let's see what happens when we do pagination for that query. And look at this guy. So imagine we have our user. Well, if our user is going to scroll to all 30,000 items, we're not optimizing a lot. But hey, I don't think 100% of the users are going to do this 100% of the time. I think, or I bet, that the majority of users actually will say, you know what, after 5 button clicks, I'm sick and tired of it. Now I'm done.
This is gonna last only 4 times. Okay, perfect. So this thing that you mentioned about connection pooling and everything, it's automatically handled by the SDK that we provide, right?
Exactly. You don't have to do anything for it. It automatically makes the most use of your connections.
But I hear a best practice here that you should probably do a warm up when you are warming up your application. That make that connection so that you can get the Cosmos DB connectivity up and running. Awesome, thanks.
Yeah. Don't destroy the Cosmos client object every time. Just create it once, cache it, and reuse it, because you can see the difference here.
Right. Yeah, and of course, dependency injection is helping towards that.
Yeah, exactly. Yeah, but now back to our query problem. Here, look at that. We have greatly optimized our query. If a user clicks just twice, instead of consuming 938, we're going to consume only 7 RUs. I love that. 7 RUs. That's awesome. And it also makes it easier for the application, because it needs to deserialize a much smaller response object than if we would return a tremendous amount of items, right?
Nice.
All right. Now let's go to our final query. Back to the browser. Here we are. Final query, which is this guy. So let's execute it.
Perfect. So basically, we are here. We are selecting the score for a participant, for a specific marathon, for and we know everything, right? This is one RU. This is what you told us before.
Yeah, that's a good point, Andreas. That's a very good point. So look at this one indeed. We're looking up participant for an event 188 and the specific participant ID. So Andreas, unless you clone yourself, which would mean you're running twice in the same marathon on the same date, this is always going to return a single document, right? And not more than a single, right? And which is true. So let's examine the query stats.
Whoa.
That's not one. That's not one. It's going to be 3, which is actually more or less. So sometimes it's a bit less than 3. Depends a small bit, but around 3-ish is the most optimum query you can execute actually. And we can also see that in the stats. So if you scroll a bit down, we see there aren't, well, it's just a couple of bytes, 0 to 30 milliseconds, something which is unmeasurable. 0.03 milliseconds document load time. So this is super optimized from a query perspective. Is there nothing what we can do, huh?
But this also shows something, that basically there is a querying engine. So basically, although it is a single record, we are hitting a specific logical partition, so a specific physical partition, and we are specifying index columns there, participant ID and event date. We still have to do the querying. The engine will have to be involved instead of what you mentioned before, something like when we were defining one RU, right?
Exactly. So let's take a look at what we can do, because again, this is something you cannot do from the query perspective. A query, like Andreas just said, whatever it is just a query, and we can tune the query tremendously, like in this case, but it remains a query. There is also, like explained before, a point read operation, and this is something you can only do from the application. In order to do that, it requires just one line of code actually. In order to do that, we need the event name and we need the document ID. Those two variables, or those two properties in our case, so the partition key, which is the event name, and the unique ID of the document, allow us to do a lookup. And a lookup is not a query. It's going to be a read item, as you can see, where we just read the item, and that's all.
Perfect.
And if we would execute this, we can see it already here. We get a 1RU operation.
Perfect. So basically, in a website where we want every participant to see for a specific event how he did, we would probably store his this ID somewhere so that we could do this lookup directly and then have just 1RU as a cost, right?
Right.
Perfect.
Right. And this doesn't sound much. I got down from 3RU to 1RU, which is only 2RUs. But if, well, every RU counts, right? But if you are executing this query thousands and thousands of time each day, or maybe even thousands of time each minute, those 2 RUs are going to count, because it's going to mean I can do more for the amount of RUs I've provisioned. In our case, 4,000. Or I can say, you know what? I'm not using those 4,000 anymore. Let's put it to a lower figure. Let's make it, for example, 2,000, which makes my Cosmos DB instance cheaper. So it's always good to get the most of your instance by applying those optimization.
Awesome. And I think so far we have covered a lot about querying optimization and how, when I'm designing an application, I can actually fine-tune those queries and optimize either the cost or the performance of the Cosmos DB. But what if I already have a workload in production? Is there a way I can figure out whether it's working fine, or there's something I can do and squeeze some more performance out of the Cosmos DB instance I have?
Yeah, that's a good point. So yes, this, what we have done so far, is super useful for when you are in the early development stages. But at some point in time, of course, you're done with development, you're going to run a load test, or you're going to be in production, right? And then you still want to keep an eye on how is my Cosmos DB instance running. Remember the cross partition query that ran fine with 50 gigs, but What if our app is super popular and it starts to grow to 100? We want to keep an eye whether that query is not going to be inefficient at some point in time. In order to do that, we can examine Cosmos monitoring capabilities. And if we take a look at the navigation pane here, so we can scroll a bit down, and then we see this whole monitoring section, right?
Perfect. So this is basically you're on the Cosmos DB resource within the portal, and then it's the normal monitoring section that you will find in every Azure resource that you have there. Awesome.
Exactly. And there are a couple of things we can do. We can say, you know what, I want to retain or persist monitoring telemetry for a longer period of time.
Yeah. So
I want to store it.
Do you have some guidance on what type of telemetry we should be keeping for long term so that we can, monitor our solution?
Yeah, I definitely do. So when you click on monitoring settings, you see a bunch of categories. Yeah, you see them all, right? And when we want to configure monitoring, because we want to store this telemetry for a bit longer than the default 7 days, we can click here. Well, I already pre-created edit setting, and you will see that for the SQL API, a couple of categories are important, and the rest is not so much.
Nice.
So the first one is data plane request. This basically means all operations on Cosmos DB, like for example, that point read that would show up as a data plane request. Well, Mongo request, we're in SQL API, so there's no point in capturing that. If we want to examine our queries, we want to see our most expensive queries, or we want to see exactly how our queries are behaving, we need this category checks, which is query runtime stats. Query runtime stats stores all the queries, including additional information, right? Awesome. By default, however, it obfuscates the query. From a privacy, you will see strange parameter names, not the real parameter names. This is something you have to explicitly enable. When you first click on diagnostic settings, you already see this. Enable full text query, blah, blah. So once you enable that, then you can see the actual query. If you don't do this, you won't be able to see it. And in order to, yes, sorry, Andreas.
So if you really want to troubleshoot something, then this is a case where you would enable this feature.
Exactly. Then you would go to features and you would say, you know what, diagnostics full text query. I'm going to put that to on, so I'm going to enable that.
Nice.
Right? And then you can capture all your queries and see exactly what's going on there.
This is especially useful if you have a black box that was developed by someone, and then you want to optimize what it's doing, right?
So. Yeah, or when you have so many queries with slightly different parameters, and some parameters forces the index not to be used, something like that. For those situations, also very, very, very nice that you can capture the query, see exactly how much RU it uses, and then start troubleshooting that query and optimize it. Anything regarding partitions, partition key usage. So have I chosen the right partition key? Don't I have a hot partition? How many RUs am I using? So how popular is Botsikas family, or how popular is this marathon in Amsterdam? How many RUs is that particular marathon or family costing? That's what you can see here with partition key RU consumption.
You touched on the hot partition, basically that if for some reason with the partition strategy you have a couple of partitions that are too popular versus the other one, right?
Exactly.
And in which cases basically you are going into the danger of getting those hot partitions in one physical partition and then be throttled by the 10K RUs limitation, right?
Exactly. And that's right. Because when that happens, well, I can add 1 million RUs, but yeah, if it's all going to the same physical box, 10 is my max.
But is there a way I can see this I mean, if, it's my physical partition is actually red or something like that, so I can...
Yeah, perfect. Yeah, there is definitely a way. So once this is enabled, then you should also enable the metrics. We'll come to that. You can store it in Log Analytics, and you do it like this. So it gets dedicated tables. This is the most, well, the easiest way of querying all this log information. So just do it like this. And if you don't want to take a look and go deeper, we have to go back to monitoring. And you see here, there is something called Insights. And when you click on Insights, this shows us actually a pre-created workbook. So for if you are familiar or not with Azure Monitor is basically the default behind all our services for anything regarding monitoring telemetry. And one of the ways of visualizing that data yourself is by creating a workbook. And that's basically a browser-based way where you build up a workbook like this one, and then you can store that, for example, as an ARM template. So you can redeploy it many times. The services like Cosmos DB also have a predefined workbook already, and we call that Insights.
Right. And you can do things like filtering. I see there the time rates. Perhaps we can limit it only to the last hour that we were active and we were showing things. So
yeah, you read my mind.
How granular can we get? I see database. Whoa. We can go down to the container level. Perfect.
Exactly. And this is actually what you should do, because remember, we provision RU on container levels. So in order to, well, not see RU usage of other containers, we should actually down drill on the container. If we have provisioned on database level, down drilling to container doesn't make much sense, because the RU are going to be, well, randomly distributed across many containers, depending on how many you have deployed. So these metrics become a bit less valuable in that case. But for our case, we have done it on our RU level, so we just simply select the container we're interested in. And what we then actually see is an overview here. We can see the data usage. And one thing which is important from the data usage is this. So you see here the amount of documents, so space required for the amount of documents, and we see the index size. Perfect. What is important is the difference between the two, because this tells me I'm not indexing everything of the entire document.
So if I use the default settings, I would see here 95 megabytes of data and 95 megabytes of an index, right?
Yeah, basically I'm storing everything twice, huh? Right. I'm indexing all the properties. So I store everything almost twice, and it's going to be a somewhat familiar or similar figure. And this quickly tells us already, oh, we forgot about the index. Now we really shouldn't, because updating an 8 megabyte index is just faster than updating a 95.
Perfect. Right.
So that's what we can see here. Already a quick thingy. We can see here in terms of RU provisioning. I'm at 4,000, but was that really good enough? Or do I see that a bunch of requests were served off by Cosmos? So Cosmos told the client, you know what, back off. Stop harassing me. I want to first finalize what I'm doing now, and after that you're up next. No entries here. So we're good.
And see the 429 HTTP error code that you would be getting if Cosmos DB was too busy. Yeah. Awesome.
Yeah, exactly. So if you see there's a lot happening, well, this is a clear indicator. You have either provisioned not enough RUs, or you have those untuned queries consuming way too many RUs, right? And by clicking this button, we can dive a bit deeper into the real log information.
Nice.
Then we have the one which I love most, and it's normalized RU. So what this says is for this database, for this container actually, how many RUs percentage-wise are being used. And there are a couple of things which are important when reading this metric. So first and foremost, if we see that we're constantly spiking at 100%, we can take a quick look at the 429s. Spiking at 100% means I'm basically utilizing all the RUs for that time period. And if we then take a look at the 429s, you can see whether, well, that's actually not really a problem because we're at the boundaries, but all queries still get executed, or when it becomes a problem because queries are simply not executed again, but retried. It was too busy. So that's one. If we see it's on the lower side, always around 2014, this indicates us that, well, it's nice that we have provisioned 4,000 RU, but I'm only using 40% of it.
Right. So
right,
probably you have over provisioned, right?
Exactly. And why would we over provision? You are billed per hour, so even for the RUs you're not using.
Right.
So yeah, there we go. That's not fun. So in that case, you would lower the amount of RUs. Right. Yes, let's go to the second screen. So when it comes to troubleshooting a bit, the following screens, throughput and requests, are just more interesting than overview. So the throughput will tell me how many request units summed up I'm using. So you can see here how many are used in this particular time period. So here in this 1 minute, I'm using 1,120 request units. Well, I've provisioned 4,000, so I would be somewhat okay. However, be mindful. This is an indicator because look at the time period, right? The time period is 10:38 here, what I have selected. That's a minute, a full minute. RUs don't operate per minute, they operate per second. Azure Monitor cannot service per second data. It always aggregates per minute, and that's what it shows you. So see this as an indicator. It's not exactly the truth, right?
No, it's not exactly the limit that you want to provision. So if you see there something like 30,000, then you probably don't need 30,000 RUs.
Yeah.
Remember that this is a per minute representation. Awesome. Thanks, Cyrille.
Exactly. So it might be that this is a bit higher, for example, than 4,000. That could be.
Right.
And I'm still not throttled. And that is due to the fact that those 4,000 are happening on a second basis. Well, this is aggregated over a minute. So yeah, but what you should take away from this is again a pattern. If you see like a constant usage, that's perfect. That means that you have a very predictable workload. The queries which are being executed are constantly performing the same way. You don't have very expensive queries which cause spiking or and so forth. So a constant usage is really something which makes you say, you know what, I'm done. I've the perfect Cosmos DB instance here. If we see a lot of spikes, well, that could be of two reasons. It could be that my application is bursting. You know what? That leaderboard is important when there is an event, but the day after, it's going to be less important. So yeah, that makes sense. If you cannot explain it though, it's worth looking into your queries. So why is this actually consuming so many RU? Why is this spike? And in order to do this, we can scroll a bit down through the metrics. So if we see a spike like this, yeah, we can see exactly how many percentage of the RUs are being used. So we used around 60% here for these 1100. If you see this also against the 100, well, okay, then it might be that we're doing too much for what is available.
Whoa.
Yeah.
Why do we have this red there?
Good point, Andreas. So what I did is when I created this collection, I was like, yeah, let me just provision 20,000 RU and then go back to 4,000. And what you immediately see is even if I'm not storing that data, just by provisioning 20K RU and going back, you are going to have two physical partitions.
So basically, you provision 20,000 RUs, which means that basically you forced Cosmos DB to provision for you two physical partitions in order to have 10K and 10K. And then, although you scale down, you still got those two physical partitions, which are then limited by 4K because this is what you're paying currently.
Exactly.
So this means all your logical partitions are actually in one partition, and this is the hot physical partition that we see there, the 100%. Basically, all our queries are hitting that physical partition there.
Exactly. And now, well, it looks red. Red is always a warning sign. At least in this workbook, it is a warning sign, but with the emphasis on warning, because this still doesn't mean I'm in a bad shape. And in order to understand whether or not, I scroll down again. Now I see the RU consumption per physical partition key. Per physical partition, scratch the key, per physical partition. So I see here for my popular one, number 2, as you can see, I still see I'm only using 60%. Here I have a spike with 100 when I run these very expensive queries. Here I have a spike again, but I'm pretty good. If you, however, see your bunch of physical partitions here, and you see that one is always at 100, and the other ones are pretty low, always, yeah, then you have a hot partition issue. And there are a couple of ways to fix that. One is announced as built to redistribute partition keys. You can see that at the build videos. It's now in preview, or we can do that by tuning our queries. All right.
And down below, you are seeing the link that contains the learning module that we are presenting so far. And there are a ton of links where you can deep dive even deeper on the topics that we are discussing right now.
Yes. And that brings us to the end. So we have learned about data modeling. We saw how to tune queries. We know now how to interpret monitoring, where to look out for. So nothing stops us from creating a beautiful, well-performing, low-cost Cosmos DB instance. And with that, this learning session comes to an end. I really want to thank Andreas. It was a great time with you. We should do this many more times. And for all the participants, please go to this collection. You can go through all the content whenever you have time.
Yeah, and don't forget, this is a series of events that we are scheduling. So, Cyrille, if you want, you can join me in a machine learning one that I'll.
That sounds like fun.
And of course, this is the link. This is where you will see all those episodes that we are filming. There is many thanks to our moderator in the chat window who has been taking all the questions and been giving answers. And yeah, thank you so much for your attention.
Yeah, and with that, we conclude our session. Thank you, guys. See you later. Bye-bye. Oh, we still have 4 minutes, by the way.
We can take live some questions.